All right, today we're going to delve into a little bit more probability as a warm-up. This is an SAT or ACT prep question. This is much like something that might be asked on the ACT or SAT. If in a typical order of bricks, 5% are delivered broken, how many should be ordered for a project requiring 2,500 bricks? Okay, so step one when tackling a standardized test question is, do you understand exactly what the question's asking? So when you order bricks, apparently 5% are going to show up broken. If you know that you need 2,500, how many should you order so that 5% can break and you'll end up with 2,500? Go ahead and pause this for 60 seconds and then come back. Okay, so here's what we know. Whatever the order is, 5% of those show up broken, which means 95% show up unbroken. So if I know that my order times 95% needs to be 2,500 bricks, how do I find just the order? Well, I'd probably divide both sides by 95%, which means divide by 0.95. If I divide by 95%, then the order that I need to place should be 2,500 divided by 0.95, which you get 2,631.58 bricks. Obviously, you can't order 0.58 bricks. So I would say that the order, bare minimum, would need to be 2632. Now, if you were actually doing this, you're probably going to assume that it's not going to be exactly 5%. You'd probably order 2650 or something. But if we're assuming that it's exactly 5%, 2632 should be enough. Okay. How many different ways can 3 books be arranged on a shelf? So I've got 3 books here, green, blue, and red. We'll just call them green, blue, and red for now. In math, we call each specific arrangement, where order is important, a permutation. We'll talk a little bit about the difference of order later. So for now, let's just start by listing all the different possibilities for where these books can go. Okay, it's called a sample space, an order of all the different ways we can organize things, all the different possibilities is called the sample space. So let's start with what we have. Green, blue, red. Okay, now let's keep this one in the same spot. So the other option would be green, red, blue, right? Now I can't rearrange while keeping green in the front. So let's change the one in the front. Let's go blue up front. So then I could go blue, red, green. I can keep blue up front and go blue, green, red. And then you realize I can't do anything else with just the red and the green. So now we need to change and have red be up front. So I could have red, blue, green, or red, green, blue. Every book has been in the front, and we've had every option where each book is in the front. So this is going to be it. So there are 6 possibilities. Now that works, but it gets kind of messy. So let's be a little bit more clever in the ways that we count. How many? Let's say we're organizing these, left to right, not up and down, but how many different options would we have for the leftmost book? Well, I could have a green book, a blue book, or a red book, so there are 3. For the book in the middle, how many options are there? Well, I've used one for the book on the left. I don't know which one, but I've used one of the books. So now there's only 2 books left. Once I've placed the middle and the left books, there's only 1 book left. There's only 1 spot left. There's only 1 book that can go in the right spot. So this method, if you notice that we take 3, 2, and 1 and multiply them together, what do we get? That same 6 for the 6 ways we can organize the books, right? Multiplying a number by each integer less than that number has a special name because we use it in probability so much. So 3 times 2 times 1, or 5 times 4 times 3 times 2 times 1. We call it 3 factorial, and we write it like this, 3 exclamation point. So 6 exclamation point would be, or 6 factorial would be how you'd read that. Would be 6 times 5 times 4 times 3 times 2 times 1. A major application of factorial is in counting, in finding the number of different ways to organize things. But there are other applications also. So whenever you see a number with an exclamation point, it means factorial, And this is what it means to do. Start with that number and multiply by that number and every integer, every positive integer less than that number. So 12 factorial would be 12 times 11 times 10 all the way down to 1. Okay. Obviously, these numbers are very large. So for example, 3 factorial is 6. 4 factorial is 3 factorial times 4. So these numbers keep growing very, very quickly. As you're going to see, counting, which you might think is very simple, is actually a very difficult mathematical skill. Now, just counting objects, yeah, no, that's not hard. But counting the number of ways we can organize things gets very difficult very quickly. So we need to use some sophisticated mathematical structures in order to do that. Okay, so the factorial of a positive integer is the product of the positive integers less than or equal to that number. So 3 factorial, 3 times 2 times 1. 6 factorial, 6 times 5 times 4 times 3 times 2 times 1. 0 factorial is defined to be 1. So this is one place in mathematics where we just decided 0 factorial needs to be 1. And one way you can think about it, if you're thinking about it in terms of the way to organize things, right? So we had 3 books, and we needed to organize them. That was 3 factorial ways to do that. What if I have 0 books? How many, whoops, that's not a 0. How many ways can I organize 0 books? Well, it's not 0 ways, right? I mean, you could have 0 books on a shelf. There's one way to do that. So 0 factorial is defined as 1, and that's something you're going to want in your notes. Okay, so the factorial tells you the number of ways you can arrange n items in a line. So for example, 1 factorial is 1. There are no positive integers less than or equal to 1 other than 1. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. 7 factorial's value is very large. And in this case, 7 factorial, well, in every case, but 7 factorial is 5,040. 7 times 6 times 5 times 4 times 3 times 2 times 1. 0 factorial, like we talked about, is 1. So yes, 0 factorial and 1 factorial have the same value. If you think about organizing things on a shelf, it actually makes sense. How many different ways can you organize one thing? Well, just the one way you can put it there. How many ways can you organize a stack of 0 things? Well, just the one way. You just don't have anything there. That's the only option. Okay. What if we start dividing these or doing various operations with factorial? So let's do 6 factorial over 4 factorial. One way, or the easy way to see what's going to happen is to write these out. So I'm just going to write out all the factors. And you'll notice something right away. There's a 4 on top and a 4 on the bottom. And then there's a 3 on top and a 3 on the bottom and a 2 on top. And then the 1s, even though the 1s don't really do anything. All that's left is the 6 times 5. So 6 factorial over 4 factorial is just 30. Okay, now if you have a TI calculator, TI-83, TI-84, TI-84CE, TI-89, there is a button in the calculator for factorial. You're going to choose the button that you want, so 6 or whatever, and then you're going to hit Math, tab over to the right until you get to PRB, which stands for probability, and then option number 4 is an exclamation point. Okay, so if you have a TI calculator, that's one way to do it. I believe the iPhone and Android stock calculators, when you turn them sideways for scientific mode, I do believe there is an exclamation point for factorial. You can do it like in Desmos too, in Desmos.com. You type the number and then the factorial, it'll tell you what that value is. But you can always recreate it yourself just by typing in all the values. It just takes a minute. A student tells his friend the password for his phone uses the numbers 5, 3, 2, and 1. How many combinations are possible? So let's say your buddy tells you the combo for their phone, and then you forget, but you remember that these are the 4 numbers, you just don't know what order. How many possible combinations could you have to enter in order to come up with these? Well, think about it. There are 4 buttons you need to enter, right? How many choices do you have for that first button? Well, it could be any of those 4 numbers. So the first number could be any of the 4 things. The second digit in the password can only be 3 of these things now, because you've used one of them. The third can only be 2 of them, and then there's only 1 choice left. So no matter which one you start with, you have 4 choices. After you choose 1, there's only 3 choices left for the second number, and then 2, and then 1. So the possible combinations, if you know which 4 numbers go into it, are 4 times 3, which is 12, times 2, is 24. There are 24 possible combinations. Now, what if you didn't know the numbers that go into it? So you've got a 4-number passcode. Let's say you don't know. How many digits are there for the first thing? There should be 10, right? There are 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. How many are there for the second thing? There's still 10, right? Because you don't know. It could be a repeat number. You have no idea. So you can see that if you don't know what they are, this isn't a factorial, but we can still use that counting principle. It's called the fundamental counting principle. It's going to be 10 to the 4th, or 10,000. If you don't know somebody's passcode, but you know it's 4 digits, there are 10,000 options. If you know which of the 4 digits, or what the 4 numbers are, but not the order, it cuts it way down to 24. So obviously not knowing those values makes a big difference. Number 2, a travel agency offers an Italian package for visits to 5 cities. The customer can pick the order of the cities. How many different packages are possible? Okay, so we're going to 5 cities. 1, 2, 3, 4, 5 cities. How many choices do I have for the first one? Well, I could go to any one of the 5 cities. Then for the second one, 4 cities, 3 cities, 2 cities, 1 city. So another way to say that would be 5 factorial. Okay, so 5 times 4 is 20, times 3 is 60, times 2 is 120. There would be 120 different vacations that you could piece together just by rearranging the order that you visit those 5 cities in. Okay. Let's make this a yo-yo here. Okay, so let's say this is a yo-yo. I don't know if you can see that very well. Go ahead and pause this video, take maybe 2 or 3 minutes, and see if you can come up with the answers to these, and then go ahead and unpause. Okay, how many different batting orders can be formed for a 9-person baseball team? Well, if there's 9 people on the team, you've got 9 spots, 1 person to fill each spot. How many choices for the first person? First batting spot, 1. Or 9, excuse me. After you've chosen that person to fill the first slot, how many can go next? If you're not very familiar with baseball, that's okay. I'm going to give you a hint. Everyone has to bat before the next person can go, or before somebody can go twice. So we've got 9 slots. We have to use all 9 people, so we're going to have 9 choices for the first slot, 8 choices for the second slot, 7, 6, etc., etc. So 9 factorial would be the number of spots that are available, or the number of ways to organize this team into a batting order. So 9 factorial has a value of 362,880, 362,880 different batting orders. And that's if you only have 9 players. Now, I've never seen a baseball team with only 9 players. You always have subs, right? And they have to be in the lineup too. So really this number is getting astronomically larger every time you add a person. If we add 1 more person to this, that'll be a 10th person. We multiply this number by 10. So if you throw 1 more person into that batting order, into the team, you have 10 times as many lineups already. And then the next person will be 11 times that, and then 12 times that. So you can see how fast these factorial values will go. Okay, number 2, simplify without a calculator. Obviously, if you're using a calculator, you type 13 factorial divided by 12 factorial. But if you can't do that, it's still not hard, right? So here's what we got. I'm going to run out of room. We know that that goes down to 1, okay? Down here, we just have 12. And again, I'm going to run out of room because I didn't space this very well. It's okay. Notice there's a 12 in the top and bottom, and then an 11, and then a 10. And you can see that that's going to happen because the rest of those numbers are going to match up. So really, from 12 down, I'm not supposed to be circling that, from 12 down, all of these values cancel. All that's left is 13. Okay. So you can see this is going to happen with the 9 and the 7 too, right? We're going to have 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And the denominator, 7 times 6 times 5 times 4 times 3 times 2 times 1. From 7 and down, those numbers are in the top and bottom. So whatever this number is, it's in the top and bottom. I can factor it out, leaving 9 times 8, which is 72. What if in that Italian vacation package they offered 5 cities, but you could only visit 3 of them? However, you still pick the order. How many available packages are there now? So choosing our first location, how many choices do we have? Well, we have 5 of them. Stop number 2, we're down to 4 options. Stop number 3, we're down to 3 options. We're not going to visit all the cities, so we don't take this all the way down to 1. It's still kind of like a factorial, but we're not using all the values. One way we could write this is 5 factorial over 2 factorial, because the 2 and the 1 need to get factored out. 5 times 4 is 20, times 3 is 60 different vacations that we could take, visiting 3 cities with 5 choices. Okay, so this is what's called a permutation. The number of permutations of n objects taken r at a time is the quotient of n factorial and n minus r factorial, meaning quotient meaning division. So if we go back to this example just for a second, the number of things we have, whoopsies, the number of things we have is 5, and the number of things we're choosing is 3. So the permutation, the number of ways to organize this, is n factorial over n minus r factorial. So 5 factorial, n minus r is in parentheses, n minus r, 5 minus 3 is 2, 2 factorial, which is what we wrote over here. Okay, so you are absolutely going to want this in your notes. N is the number of options, number of things. R is the number we're choosing. Okay, so number of things and how many we're choosing. You can use a calculator for this also. Again, if you have the TI calculator, you need to type the number that you want first, so the number of options. Then you hit Math, tab over to PRB, which represents probability, and then option number 2 is this lowercase n, capital P, lowercase r. So it's showing you which order to type things in. Type the number of things, then find NPR, and then type the number of objects. So in that previous example, it would be 5. Then I go to Math, PRB, number 2, and then I'm going to type 3, because we're choosing 3 of those cities. Then hit Enter. If you're using a TI-84 or 89 and you have Math type turned on, or Math print, then you're going to choose that Math probability option first, and then it'll be n comma r. I can answer any questions about that if you have them, but you don't need a calculator to do this. This formula is not that complicated. Okay, so use the equation to compute the following, and then if you have one, check it with a calculator. I'm also going to tell you that on Desmos, so www.desmos.com, you can also type these numbers in. Okay, so you're just going to type in NPR, capitalization matters, parentheses, 6, 3, and it'll tell you in the lower right-hand corner equals whatever the value is. Okay, so you can use Desmos if you have access to a computer but not a TI calculator. Most of your built-in phone calculators will not have the permutations formula built in, but if you download a calculator emulator, a graphing calculator emulator, it should have it. Okay, so this is going to be our n, this is going to be our r value. So the number of permutations is 6 factorial over 6 minus 3, that quantity, factorial. So it's going to be 6 times 5 times 4 times 3 times 2 times 1 all over 6 minus 3 is 3, 3 times 2 times 1. These will cancel, leaving me just 6 times 5 times 4. 6 times 5 is 30, times 4 is 120. Over here, again, n and r. So permutations are going to be 4 factorial over 4 minus 1 factorial. So that's going to be 4 factorial over 3 factorial, which, think about what this is going to be, 4, 3, 2, 1, and this will be 3, 2, 1. All that's left is just the 4. Okay. And that makes sense. I'm trying to figure out how many ways I can organize 4 things if I'm only choosing one of them. Well, I choose the first thing, that's one way. Then I choose the second thing, that's the second way. Then I choose the third thing, that's the third way. Or I choose the fourth thing, that's the fourth way, and that's all there is. I'm only choosing one thing, so the order of those things can't matter. If you're only choosing one thing, it's the number of permutations is just going to be how many things did you have. Okay. Soccer team has 11 players. How many ways can a coach select the order of 5 players to take penalty kicks? So at the end of a soccer game, if it's tied, you just start taking penalty kicks, and whoever scores best out of 5 wins. So we need 5 players out of those 11. For the first kicker, I can choose any one of my 11 players. For the second kicker, I've already chosen one. I have 10 left to choose from. For the third, I've chosen 2 of them, which means I have 9 left. So you can see where this is going, right? Everyone's got a kick before anybody can go twice. So it's going to be 11 times 10 times 9 times 8 times 7. I'm going to grab my calculator for this. 11 times 10 times 9 times 8 times 7. It's going to be a lot. If I'm going to use a calculator, NPR of how many things are there? Well, there are 11 players to choose from. How many do I need to choose? Just 5. So 11 factorial over 11 minus 5 factorial. Now that has to be in parentheses, right? So that's 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Barely squeaked it in. Over 11 minus 5 is 6. 6, 5, 4, 3, 2, 1. So let me change my color here. Everything from 6 down is going to go away, right? Because it's in the top and bottom, which means all that's left is 11, 10, 9, 8, 7, which is exactly what we had over here. So if you plug that into the calculator, you will get the exact same 55,440 ways to choose the kickers. The computer program asks you to make a 7-character long password using only numbers and letters. However, no character can repeat. That makes it sound harder, but that actually makes it easier. How many different combinations are possible? So go ahead and pause this, take 2 seconds, or 20 seconds, whatever it takes, and then come back for the answer. Okay, hopefully you figured this out. We have 7 slots, right? So that means I'm going to choose 7 things. The number of things I have to choose from is the only tricky part. It says a 7-character long password using numbers and letters. So how many letters are there? Hopefully you said 26. How many numbers are there? A lot of people want to say 9, but there's actually 10 if you count 0, right? So there's going to be 26 letters and 10 numbers for a total of 36 things to choose from. However, most passwords allow capital numbers, or excuse me, capital letters, right? And there's a difference in uppercase and lowercase. We'll do it twice. We'll do it with this one, and then we'll do it again with the other. So this would be 36 factorial over 36 minus 7 factorial. So 36 factorial over, what, 29 factorial? Now, if you don't have a calculator that can do this, the function built in, you can set this much up, and every calculator should be able to do this. Every scientific calculator is going to have that factorial option. Okay, so 36 factorial divided by 29 factorial. Everybody run that on your calculator if you didn't before. I'm punching mine in right now. I'm getting 4.21 times 10 to the 10th power. There are an incredible number of passwords. Now, if we did it with the capital letters allowed, so there's 26 letters, but then all the capitals make 52, plus the 10 numbers, there are 62 possibilities. If we do it that way, now let me punch this in real quick. The number of passwords is going to go up significantly. Now I'm going to have, if I do it this way, 2.48 times 10 to the 12th. Now this number is smaller. However, the exponent is 2 numbers bigger. So this is a 4 with 10 decimal places after it. This is a 2 with 12. So this is over 100 times bigger than the one above it. Okay, so it's definitely going to matter whether or not we allow those capital letters. So when you see a password that allows capitalization, that password can be much more secure, because if you're just going to try and guess what it is, that looks like this. Let me write this whole number out just for giggles. 2, 4, 7, 8, 6, 5, 2, 6, 0, 6. I need to go 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's thousands or hundreds. Thousands, millions, billions. You'd have to try 2.478 billion passwords before you just figured it out. if it was the last one, right? So you have a 1 in 2.5 billion chance of guessing that password if you allow the capital letters. Otherwise, it's 1 in 4 point, or if it's at 42 million, I guess. So significantly different. Uh, use the equation to compute the following, and then check with the calculator. And then there are 300 people in the senior class. How many ways can you select a class president, vice president, and secretary? Again, pause this until you're done, and then come back. Okay, so permutations of 7 things chosen 5 at a time should be 7 factorial over 7 minus 5 factorial, or 7 factorial over 2 factorial. So 7 times 6 times 5 times 4 times 3 would be all that is. So 7, checking it on the calculator, 7 factorial divided by 2 is essentially what we're doing. 2,520 ways to do that. 300 people in the senior class. We want to select these officers. There's a class president, a vice president, and a secretary. That's 3. So what I'm really doing is permutations of 300 people taken 3 at a time. Okay, so in the formula, that's 300 factorial over 300 minus 3 minus factorial, or 300 factorial over 298, 7 factorial, which means it's really only 300 times 299 times 298, right? Because 297 and down are gone. Or think about it from the fundamental counting principle. We have 3 slots to fill. I've got 300 people for the first. I've chosen a president. Now I only have 299. After I've chosen the president and the vice, I only have 298 positions left, right? So those are all big numbers. But what it gives us is 267,306,000. 26,730,600. So these things grow very, very quickly, as I mentioned, and these numbers get very big very quickly. But if you have a calculator with permutations built in, you can punch something like that. And if you don't, you can take it to this step and then do it, because you should be able to get to the factorial. If you can't do that, you should be able to take it one step further and figure it out. Everyone who's able to watch this video, though, has internet, and Desmos.com is free. You can do factorial, or really even this part, right? Like I said before, let me just go back to that page real quick. Where was that? I don't remember where I showed you. Maybe I'm not going to be able to find it. Okay, I'll show you again. There it is. www.desmos.com. This is what you're going to type in. Lowercase n, capital P, lowercase r, parentheses, n things, comma, r at a time, close parentheses. It's going to give you like an answer bar down here, and in this corner is your answer. Okay? If you have any questions about that, let me know. Feel free to rewind and rewatch any part of this video, and then have a great day.